Hi everyone. Welcome to our first lesson for Calculus 1. In this first lesson, we're going to be covering the tangent and velocity problems. Now, as an introduction to this section, what I want to do is I want to talk about what it means to be a tangent and what it means to be a secant line when we're talking about a point on a function. Now, I'm going to start off with a tangent. So, looking at a tangent line will intersect or will touch the point at just that one specific value. In other words, it will get us a really good approximation for that function if we look at the rate of change of that line at that given point. So that's always beneficial. And I'm going to call this tangent line L1, which will be line 1. Now, I'm also going to give a depiction here of a different line, which I will then call line 2. Line 2, as you can see here, intersects the graph and it fully goes through that graph. At this point in time, this is called a secant line. Secant lines can turn into tangent lines, and that is going to be what we want to focus on at a later time. But for now, we can see that we have a difference here between two lines. Line 1, which is tangent, line 2, which is a secant line. So if the question was to ask whether we can find a rate of change for that function, we would then need to investigate one line over another. We would want to investigate the secant line, or we would want to investigate the tangent line. Either way, our results, as you will come to see, will be the same with the help of calculus. So as we proceed in this course, I want to make sure that we can identify that the secant line here will intersect the graph at 2 points, which we see here. So when we're looking at this, we then have to interpret, well, what is it that we are going to be observing? Notice that if I want the rate of change for this function f of x, I can approximate that rate of change if I then start looking at an average rate of change for this secant line. So I am going to write here that the secant line can or will approximate the rate of change it will approximate the rate of change for f of x, for f of x, and I'm going to say that this is point A, that way we can have a reference. It will approximate the rate of change for f of x when any x values are near point A. So this now gets us into that whole topic of what does it mean to be near that point? Well, what we want to be near is going to be relatively close. It's going to be relatively close, implying that it's as near as you want it to be. The closer, the better. The further, the more not accurate your results will then be. So what we want to do then is we want to use this average rate of change that we've then seen back in college algebra, and we want to use that in order to extract what it is that we're going to be looking for. Now, what's really nice about this is that that average rate of change is really just going to be the slope of the line L2, or your secant line, and when we want to find that slope, we want to choose the other point close enough to point A that it'll give us a really good result. So again, we want to find that slope of the secant line in order for us to get a really good approximation for what that rate of change is going to be. Now, how do we find the slope? Well, in order for us to find the slope, then I am going to write here slope of the secant line. Remember, m is for slope, and the slope of the secant line is just going to be y2 minus y1 divided by x2 minus x1. It's as straightforward as that. Now, do we want to do this in a more general sense? Sure, we would like a more general sense of what appears to be happening. So what we're going to do instead is we're going to say, well, if we have two different points, say that we have some value here for A, and I'm going to give this a coordinate. Let's just call it x1, comma, f of x1. And again, we have our x values and our y values. And let's call this second point x2. That's your x value. And then your output, in other words, your y value, will be f of x2. In this instance, when we're looking at x1, this portion is y1. And for the second point, this portion is y2. In that instance, our slope of the secant line now becomes something really nice, which is f of x sub 2 minus f of x sub 1, all divided by x sub 2 minus x sub 1. And if you recall, this is your average rate of change that we analyzed back in a college algebra or back in a pre-calculus setting. And this is indeed what we want to use in order to start evaluating these velocity problems or these tangent problems. So remember this formula, as it will be very beneficial. There is another form of the slope of a secant line, and that's if we go ahead and if we fix a certain value. So in that instance, we actually get what is known as the difference quotient. And the difference quotient is still a manipulation of this fact here for this slope. So I'm going to write here the difference quotient. And this difference quotient, again, it's going to be beneficial for us, where we have f of x plus h minus f of x, all divided by h. Both of these values are exactly the same, whether we're looking at the slope of a secant line or whether we're looking at a difference quotient. So we have to make sure we keep that in mind. Now, on to an example. And when we go on to that example, we're going to make sure that we keep using either one of these formulas, where I will more than likely prefer this first formula, which is the slope of the secant line, as you're going to see with this next problem. So let's let our internet magic happen, and when we come back, I will have the problem and we will continue. So here we are. Internet magic, the problem already appears, or magically appears. So we want to now try this example where we're given a point P that has coordinates 0.5 and 0, and it's going to lie on the curve y is equal to cosine of pi times x. There's 4 parts to this, part A, B, C, and D, and part A is broken up into 8 separate parts. So let's start with part A. If Q is the point x, comma, cosine of pi times x, use your calculator to find the slope of the secant line PQ, correct to 6 decimal places if possible, for the following x values. Okay, so I'm going to stop right there really quick. They're telling us that we have this line segment that goes through the points P and Q. And they're telling us also that point P is fixed. So point P isn't moving from the ordered pair 0.5, 0. However, the point Q is moving, and the point Q is going to move corresponding to these x values that are given down below. And these are the 8 x values that x will take on for this function. Which means if we substitute our x value for 0, then we're going to have cosine of 0. From there, we can see that cosine will be 0. Sorry, cosine at 0 will get us that cosine would be 1. My apologies. Then we would have x being equal to 0.4, making that substitution into the function cosine of 0.4 pi. We can then go through and make those calculations. So we have our work cut out for us in the sense that we know what we need to do. Now we just need to do it. For part B, we then need to use the results of part A. So we're going to use the results that we got in part A, and we're going to make a guess of what the value of the slope of the tangent line to the curve at point P should be. So once we have the work done in part A, we should be able to get something fairly close, or we should be able to see a pattern to see how we're going to estimate or how we're going to guess that tangent line or the slope of that tangent line. Then part C, we need to then find an equation of the tangent line at the point P. And then finally part D, we're going to sketch a curve, 2 secant lines, and the tangent line. So we got some work ahead of us, and we're going to start the work at this point in time. Excuse me. Let's start with part A. We know that we're going to have to create these values, and we're going to have to find their slope. So one of the first things that I want to do at this point in time is to generate a table that will not only incorporate these x values, but that will also incorporate y values and their slopes. So let's go ahead and start working with that. Let's start creating a table. All right, I'll create my table. You all can start creating your table for part A. All right, it's looking good so far. Whoops. I want to grab the ruler, not the paper. Okay. I think this should be good. Let's move the paper a little bit more. There we are. So on the first column, I am going to insert my x values. On the second column, I am going to insert my y values. And on the final column, I'll go ahead and I'll enter my slope moving from P to Q. So I'm going to write here M for slope, and then on its subscript, I'm going to write PQ, simply because this is going to be the slope for that line PQ. So I'm going to grab all of these x values that were given to me in part A. So let's go ahead and let's start that. I need 0, that's going to be the first one. Then I'll have 0.49. Then we'll have 0.499. Oh, excuse me, sorry. I made a mistake. We are all human, and it happens. The first one, 0.4. The third one is 0.49. And the fourth one will be 0.499. There we are. exactly as it was given to me here. Good so far. Great. Now, we don't have a point at 5. So what I'm going to do here is I'm just going to insert my 5 here, but I'm going to put a question mark here because this is going to be what we're trying to guess, is going to be this slope for that secant line once it reaches this value of 0.5. My apologies. Oh my goodness. 0.5. There we are. And then the rest of the values that were given to us are these 0.501, 0.51, 0.6, and then 1. So I'm going to go ahead and keep writing those down in increasing order. So this is going to be 0.5, just making sure I'm grabbing this, 0.501. There we are. Then we get cheese and crackers, 0.51. Then we get 0.6, and then we get 1. There we are. Excuse me. So now that we have this, we can go through and we can start calculating the y values that we're going to need. Now remember, the y values are going to be, in this particular case, y is equal to the function that is given to us, which is given as cosine of pi x. So here we get that y is equal to cosine of pi times x. Let's make the first substitution. What happens when y is equal to cosine of pi times x? Well, in order to view that, we're going to plug in 0. That means cosine at 0 is, yep, that 1. Perfect. Good so far. Let's keep going. Now, 0.4. Let's go ahead and make the substitution for 0.4. All right, so my next substitution is going to be 0.4. I'm going to do that work over here on the right-hand side, where I'm going to have y is equal to cosine of pi times 0.4. And when you insert this into the calculator, since we have a pi in this particular case, please enter it in radians. So once we enter this into the calculator, we'll be able to see that this gives us an approximation of 0.309017. Notice I am truncating this value only to 6 decimal places because at the end of the day, the problem was asking us to estimate this up to 6 decimal places, and I want to keep with that process. So in here, my y value is 0.309017. Very nice. And we're going to keep doing this over and over and over again with these different values. So when you make the substitution for the next one, you should get 0.031411. Make the substitution for the next one. We should get 0.003142. Again, we're skipping the 0.5 because that's what we're trying to estimate. We're going to move on to the next one, 0.501. So 0.501, making that substitution, should get us negative 0.003142. Making the substitution for 0.51, this should get us negative 0.031411. 0.6, making that substitution, should get us negative 0.309017. And finally, making the substitution of 1, Well, cosine at pi times 1, which is just cosine at pi, should be -1. There we are. Awesome. Now that we have the y values, we need to go through and we need to start finding the slope of that secant line. So remember what I said at the very beginning here and what I have highlighted in orange at the top right-hand corner of the screen. That if I wanted to find the slope of the secant line, then that means I need to use this equation here. Now, what's going to be very nice about this is that I have two given points. I have one of my points Q. Q is the point that is constantly changing. That's the one that goes through all of these x values that we just listed. However, point P does not change. Point P is actually fixed, which means when we try to find these given secant line slopes, all we need to do is figure out what the difference is between the fixed point and the point that's changing. In a sense, we can start extracting that the slope, in this case the slope, is going to be y2, which we'll classify as one of our points here. Let this be x1, y1. Let me erase this. So we're going to have y2 minus y1, which is fixed at 0, divided by x2 minus the x value that's fixed at 0.5. So all we really need now is to start making these substitutions. The first set of values, x is 0, y is 1, we make the substitutions here. Which means that in order to find this slope from P to Q, we need to make the substitution y is 1, we keep everything else the same, x2 is 0, and we keep everything else the same. Check that out. When we simplify, then we get -2. Great. And we're going to keep doing this for this one as well. We have our x1 and we have our y1. In this particular case, again, the slope is going to change, but now we can go through y2 is this new y2, which is 0.309017 minus the one that doesn't change, that's 0, divided by x2, where x2 was 0.4 minus 0.5. We input this into the calculator, and we should get, negative 3.090170. Again, a correct estimation up to 3 decimal points. Up to 6 decimal points. Great. Now that we have this, I want you all to then keep trying the rest. Keep working the rest till you extract all of those values. If you need to, put pause on the video. I highly suggest you put pause on the video. Make sure that you are extracting these values, because if you were to see this on, let's say, a quiz or an exam, I would need to see the work that you are working on. So take some time, pause the video, do it now. And I'll fill in mine as well. All right, so here is the filled in table. Now, again, what we want to do in part A is that we want to find the slope of those points, or we want to find the slope of the secant line between the points P and Q, which we did on that table. That's actually the work that we needed to do. 1, 2, 3, 4, 5, 6, 7, 8. 8 different slopes here. Now in part B is now asking us, and let me just notify that this is part A. Part B is asking us to guess the value of the slope of the tangent line at the point P, which is 0.5, 0. So in other words, we want to guess this particular value. That's the value we want to guess. So the big question is, can we analyze it? as these secant line slopes keep getting closer and closer and closer to 0.5, what value are they approaching? It's a very famous constant. Very, very famous constant. It's kind of what I like to eat on Thanksgiving. Yeah, pie. It's pie. My favorite's pumpkin pie. Now, this is what we're estimating. We're going to make a guess that part B, the value that it's approaching, we are guessing that that's going to be pi, negative pi. So I'm going to write here that we estimate that the slope of the tangent line, and I'm just going to write the slope of tangent here, is going to be negative pi. Okay, great. So that's what we're estimating to be, or that's what we're guessing to be. Part C, we want to use that slope that we're guessing now to find the equation of a tangent line. So let's work with that. I want to find the equation of a tangent line. The equation of the tangent line, well, I need to know what's the slope of that tangent line. So I need the slope of the tangent line here multiplied by x minus x1. And this is the linear equation that we're going to be using. This is known as your point-slope form of an equation of a line, and this will always help us find that equation of the line that we need. So in this particular case, let's go ahead and let's make our substitutions. Y minus y1, well, y1, we're looking at the point P, which means y1 is going to be 0. The slope that we're estimating, or that we're guesstimating, is going to be negative pi. X minus x1, which is going to be 1/2. You could leave it as 0.5 if you'd like. However, I don't like to deal with decimals too much, so I'd rather express it as 1/2. Now, if we solve for y, we now get that y is equal to negative pi times x plus pi divided by 2. Awesome. So this is the equation of the line, of the tangent line, that we're expecting to be tangent to the function that was given to us at point P. Now, I want you to kind of take that in. And the reason I want you to take that in is because this is very, very beneficial. I want you to analyze what we just did. And think about this. In algebra, or in pre-calculus, or in trig, whatever class before this, we were asked to find the equation of a line. However, they always gave us two different values, two different point values. Now, when we're asked to find the equation of the tangent line of a function at a given point, we don't need two different points. We just need one point. We need one point, and we need to know what function we're working with. That's all. That in itself is very, very impressive. So, take that in. It's a lot. Now, we're going to work on graphing this function. So when we work on graphing this function, we want to make sure we graph the function correctly, and we also want to make sure that we show two secant lines and that we also show the tangent line. So let's get into that process. I am going to get a grid going here, and this is going to be for the last part, part D. I might make this a little large, that way we can definitely see where the secant lines are and where the tangent lines are going to be. All right, here's going to be my x, here's going to be my y. Now I'm going to find some values here. 1, 2, 3, 4, 10, I want this to be 1. And I want this to be 0. Let's call this 0.5. And this to be 1. Now, if you need a refresher on how to graph trigonometric functions, I would highly suggest that you review that material. And here we are, -1. So let's go ahead and let's start graphing cosine of pi times x. There we are. Okay. Now, notice I don't want to draw or graph any more of these functions or any further of this function for cosine of pi times x, specifically because the point in question is going to be point P, and if you remember, point P had the ordered pair 0.5 comma 0. Its tangent line has a negative slope, and the negative slope is pi, which means, that as we start looking at this tangent line, this is going to be the tangent line. There we are. So there is your tangent line. Now, let's see if we can extract a little bit more. We need to find two equations to graph, and that's going to be two equations of the secant lines. So I kind of see two secant lines that I like, and I will highlight these, one of them in green and the other one in orange. I'm looking at those two equations simply because those two equations stand out to me that they will be on the easier side to graph. So let's start extracting those equations. So for the first ordered pair that I'm going to be working with, that's going to be 0, 1 as such, 0, 1, and we know that the slope was -2. So we know that the slope was -2. Okay. Now that we have this, we can go through and we can find the equation of the line, or we can simply just graph the point. So at 0, 1, here we are, has a slope of -2. So I go down 2, 1, 2, and then over 1. Okay, so down to 1, 2, over 1. Here we are. Oops. I'm trying to get this right on the money. There we are. So this is that secant equation that we have where it goes through the point 0, 1. Now let's look at the next equation. Well, the next equation, or the next point here, is 1, -1, and it has a slope of -2. So I'm going to go over to 1. So I go over to 1, down to -1, has a slope of -2, and guess what happens? It's the exact same line. So that's kind of neat. It's kind of beneficial to say that both of these secant lines are superimposed on one another. So that's secant line 2. And then we also had secant line 1. So again, we have two secant lines and we have a tangent line there, which is really, really cool. So there you are. That is how we are working with these types of problems. Now, if we wanted to, at the end of the day, could we have streamlined this process? Yeah, we definitely could have streamlined this process a little bit more by identifying that one of the points, if you look at my cursor on screen, that one of the points of the slope of the secant line is fixed. The other one could just be the equation of the function. And what I'm saying here is that if we had one of the points fixed, so I'm going to say other possibility, is that the slope of the secant line could have been thought of as your y values, cosine of pi x, minus the y value, which was 0, all divided by, whoops, let's not make that line ugly. There we go. Divided by x minus 0.5. And in this particular instance, you would then see that all we're doing is we're taking cosine of pi times whatever input, and then we're taking the input x and subtracting 0.5. This would have been a nice way to streamline the whole process. That way we don't have to keep plugging in different numbers. That way automatically we can just say, hey, my next x value, let's plug it in. My next x value, plug it in. And the process again becomes more easier to work with. So there are different options to work with here. Pick the one that you like the most. All right, so that wraps it up for section 1.4. I hope you all enjoyed this lesson, and I will see you all here for the next one.